Hello, can you hear me?
Yes, sir.
Okay, great. Okay, so we're, I guess, good to go. You should be seeing my desktop. Is that what you're seeing?
Yeah, we can see it.
Okay, yeah, I'm going to use the desktop like the screen in class. So my hope is that I want to show you. There's a new homework assignment up on the website, so I want to show you. The first thing we'll do is go through this homework assignment like we usually do. So I'll go through the idea of what the homework assignment is. So I'm probably not even going to turn on the video for me. I hope that's okay. So mainly, I think what I'll do is just show you the desktop so that you can see the code and see what the assignment is. Okay. And um, oh, first of all, if somebody has questions, you can just unmute yourself and ask a question, right?
Yes.
Okay, so I was just assuming, I don't know if there's a way that you can raise a hand or something like that. So I assume that the best way, if you have a question, is just say, you just interrupt me and ask a question. Because otherwise, yeah, if I just keep doing all the talking, like in class, you guys ask a lot of questions and that's good. That makes things go better. So if you have a question, just go ahead and interrupt me. So yeah, I don't know if there's a way for you to raise a hand, but yeah, I think just interrupting me would be fine. Okay, so we're going to meet like this Monday and Wednesday. I gave you a link to this meeting. As far as I know, that link will be the same link for every meeting, so you won't have to get a new email or a new link each meeting. Okay, so that should, I hope that's the way it works. And we'll meet Monday and Wednesday, just like before. I'll be setting up something for office hours, and also, as usual, you can send me emails whenever you want. You can ask me through an email if you want to have it like a Zoom meeting. So if you want to ask me questions more directly rather than just through an email, we can always set up a quick Zoom meeting. Okay, so if you want to meet with me like that, send me an email. Ask, try. We'll arrange a time. And is there anybody who's got a concern right now? Is there anybody who's got a problem? Is everything working okay for everyone? Okay. Okay. I hope everything's working okay. All right. So, okay. So let's go over a little bit about the next programming assignment is. So there's a new programming assignment. It's up on this page here. The assignment's got a long description. Okay, there's a lot to explain in it, but it's not a long programming assignment. There's only a little over 100 lines of code to write, but there's a lot of ideas. Okay, and what you're going to be writing is a simple scheduler. You're going to implement a simple scheduler. You're going to schedule processes on CPUs. Okay, so I've downloaded the zip file for it already. Okay, here's the zip file looks like. Okay, and the assignment's just got a few files in it. Okay, here's the here's the file that you're going to be writing. You're going to be writing that one, homework3.c. Okay, that's the scheduler, and you're scheduling this program here. Okay, I wrote that program. There's a source code for it. You can look at it. You don't really need to, but this is the program you're going to be scheduling. So let's see what that program does. If I open up a command prompt here, okay, I can run this program compute. Okay, and if I run it, it says usage compute seconds. So run it again and say like 4. That runs for 4 seconds. Okay, so that program runs, and what it does is it uses up 4 seconds of CPU time. So it's just, and it tells you a little bit of information, like it told you what it was process ID 11576. We'll say a little bit, it was running on all the CPUs. That's what its Affinity Mask was. It was actually running, you can see it bounced around on processor 2, then it was on processor 8, then it was on processor 2 again, then it was on processor 9. You can see how it bounced around. We know that if we look at the task manager, this machine has, we set up task manager. This machine has 12 cores. So a process could bounce around the cores as much as Windows wants it to. Windows gets to decide how much processes bounce around cores. Okay, so this process we could see was bouncing around a bit. But as it bounced around, it used up 4 seconds of CPU time. And okay, you're going to be scheduling this process on CPUs. Okay, so here's a demo version of the program. So let me run the demo version of the program, and that's what you have to emulate. You have to write your code to emulate this demo version. Okay, so if I run the demo version, it tells me that the usage is run the program with a number, which is the schedule type, and seconds. Our scheduler is going to do 3 algorithms: first come, first serve, shortest job first, and longest job first. So when I run the program, I have to say which scheduling algorithm to use. So here's first come, first serve. Then it says seconds, ... That means you have like a 3-second job, a 4-second job, and a 5-second job. Okay, so my scheduler now is supposed to schedule a 3-second job, a 4-second job, and a 5-second job, first come, first serve. But there's 12 CPUs, so what it's going to do is it's going to schedule all 3 of these right away because there's 12 available CPUs. Now here's what it looks like when you run it. Okay, there's the jobs running. There's okay, pardon me? Okay. So you saw that when I ran the program, it scheduled. So it's going to schedule 3 jobs: a 3-second, 4-second, and 5-second job. It launched the 3-second job on processor 1. It launched the 4-second job on processor 2, and it launched a 5-second job on. Oh, notice that these over here are actually hexadecimal mass. That's processor actually 0. That's processor 1. That's processor 3. Okay, these are bit mass. So that's a hexadecimal number 2. You know, the hexadecimal number 2 is 10. That's the hexadecimal number 4. The hexadecimal number 4 is 100. So that means it was running on the CPU that was it was 100, so it was the 3rd CPU. Okay, so we're going to be working with these hexadecimal mass rather than numbers, because that's the way the Microsoft's functions that you call to set this stuff up works with these mass. Okay, all right. Now, this wasn't very interesting because I scheduled 3 jobs and I have 12 processors. What's more interesting is when I want to schedule 3 jobs and I only have 2 processors. So we've seen how to do that in class. We call up Task Manager and we find this CMD in details. So there's that CMD, and I set its affinity. Okay, I set its affinity. Now notice that this one's got a lot of CPUs. Okay, I'm going to set its affinity to just being CPUs 1 and 3. Okay, so I'm going to give my CMD only 2 CPUs. It's only allowed to use 2 CPUs now. Okay, so this window is only allowed to use 2 CPUs. So when it runs when it runs Homework 3 demo, Homework 3 demo is only allowed to use 2 CPUs. So it's trying to schedule 3 jobs on 2 CPUs. So it'll schedule the 3-second job first, then the 4-second job, then has to wait till the 3-second job is done, then it can schedule the 5-second job. So only 2 windows will pop up. There's only 2 windows popping up. Then see, when one of them died, another job got scheduled. Okay, so the scheduler is given a certain number of CPUs, and it has to schedule a certain number of jobs on the CPUs. And if it has more jobs than CPUs, it just waits till a CPU becomes free. The tricky part of this program is you have to write code that waits for the CPUs to become free. As CPUs become free, you schedule a new process on the CPU, and then you wait again for CPUs to become free. So you've used wait for single process before. in this program, you're going to be using a function called wait for multiple processes. We'll look at the idea in a minute, but you're going to be waiting for multiple processes to finish because you don't know which one of them that's running is going to finish first. Okay, let's look at some other examples here. Okay, so let me run a 5-second job and another 5-second job and another 5-second job. Okay, so what happens there is 2 5-second jobs are going to launch because there's only 2 CPUs. Then they'll both end at the same time, and then the last job will get run on one of the 2 CPUs. So there's 2 jobs running for 5 seconds. Then when they both died, then one of them, the third process, got started on the other CPU. And you can see what happened here. It ran a job on CPU 2, another one on CPU 4, and then it ran the last job on the same CPU here. Okay. So it reused one of the CPUs because when it got to the third job, it only needed 1 CPU. Okay. Let me try something here. I'm looking for the whiteboard. Oh, yeah, I'm sorry, there. Okay, you should see the whiteboard. Yeah. Remember, here's how you think about the CPU masks. Okay, let me see if I can do this. These are the bits in a binary word. So I've got 1, 2, 3, 4, 5, 6, 7. Eight bits in a binary word. Okay, so these are bits in a binary word, and a number like 3 is written in binary as 1, 1. When we talk about bit masks, that's 2 CPUs. This would be CPU 0, and this would represent CPU 1. Okay, so if you see that the bit mask is 3, that means that there's 2 CPUs. Okay. Right. On the other hand, if the bit mask is say 5, let's see. Oh, see. If the bit mask is 5, okay, we write that in binary as, let's see, 1, 1. Okay, so that would be. So what else did you want to do? So that a bit mask of 5 would mean CPUs 3 and 0. Okay, so we're going to be working a lot with these bit masks. Now it's real tricky because if you see 5, you think it might be CPU 5. Okay, that's CPU 5 over here, but that's not what a bit mask of 5 would be. A bit mask of 5 would be CPUs 3 and 0. So when we run our program, let's see. Do you see the desktop again now? How does it work? Do you see the whiteboard and the desktop both, or do you see only the whiteboard?
Just the whiteboard.
Oh, so you're only seeing the whiteboard now. Okay, so I see both. Let's see. So I guess I have to go back to. Nope, that wasn't the right thing to go back to. Now you see my desktop? Okay. I saw you see my desktop now, right?
Okay. Yeah, we see the desktop.
Okay, so you can so when you see the mask 2 here, that's not CPU 2, and that's not CPU 8. Mask 2 is CPU 1 because we start counting at 0. So mask 2 is CPU 1, and 8 is what? What would we say that was? That's I forget now. What is CPU? 8 is
CPU 3.
CPU 3. Yeah, see, 2 to the 3 because 2 to the 3 is 8. Yeah, so this is CPU 3. Okay, so this is, okay, so you have to read these masks real carefully because that's what you're going to be programming with. You're going to be programming with masks, not just the number of the CPU. It's going to be always the mask of the CPU, which bit represents the CPU. Okay, now, okay, let's look at, so, oh, here, now, notice that this thing here took 10 seconds to run a 5-second job, a 5-second job, and a 5-second job. You can do something, you can use the time this command. Inside this folder is the time this command. So you can say time this, then schedule 0, 5, 5, 5. Okay, now when I run it, there's the 2 5-second jobs running together. Now here's the third 5-second job running by itself. And then time this tells you, see, it took 10 seconds to run those 3 jobs. Okay, because yeah. Now, let's do something a little bit different. Let's look at one of the other scheduling algorithms. Okay, so suppose I run I remember I have 2 CPUs. Suppose I run a 5-second job, a 3-second job, and a 2-second job in first come, first serve order, okay, with 2 CPUs. Okay, so what's going to happen? The 5-second job is first, it'll run on the first CPU. The 3-second job is second, it'll run on the second CPU. It'll end in 3 seconds and become available, so then you can run the 2-second job on the 2-second CPU. So the 3 jobs will run for a total of 5 seconds. Okay, now check this. Okay, run it, time this. There's 2 of the jobs running. Okay, notice it took just a hair over 5 seconds to run a 5-second, a 3-second, a 2-second job. And you can see what happened here. The 5-second job was launched on CPU mask 2. Then the 3-second job was launched on CPU with mask 8. After 3 seconds, it terminated, so CPU 8 became available, and the CPU 8 ran the 2-second job. Okay, so that was first come, first serve. And the total run time was 5 seconds. What happens if I change it to shortest job first? Okay, now think, what's going to happen now with shortest job first? It'll run the 2-second job on one CPU. Then it'll run the 3-second job simultaneously on another CPU. Okay. Then after 2 seconds, this CPU becomes available. So now it runs the 5-second job. Now it's going to take 7 seconds. So by changing the scheduling algorithm, in a way, this won't be as good a scheduling algorithm now because it's going to take 7 seconds to do this work. There's how much work there is. There's actually 5, 6, 8. There's 9 seconds worth of work. But with first come, first serve, it actually did it all in 5 seconds. Now it's going to take 7 seconds. So let me run this. Okay. Okay. You can see it took a little over 7 seconds. Now there's some overhead coming in play here. So it should have taken exactly 7 seconds, but it took a little bit over 7 because there's some overhead in running the scheduler. The scheduler has to make switches between the processes. But you can see what it did. It ran the 2-second job and the 3-second job first. Oh, see how it's scheduled on the command line. I said run a 5, 3, and a 2-second job. But since I said to use shortest job first, on the output, it says it's going to do 2, 3, 5. So it reordered the jobs into shortest job first. Then it ran the 2-second job, 3-second job. Well, the 2-second job and the 3-second job will run on different CPUs. The 2-second job finished first. So then it got replaced by the 5-second job on CPU 2. And the total ended up being 7 seconds. Okay. So this is the idea. You have to write the program that does this scheduling. Now, the big questions are, how does it put a process on a specific CPU, and how does it wait for when a CPU is free and it's time to run another process on it? Okay. So let's look at some of the. Okay. Here's the explanation of the program. There's a long explanation of how to deal with this stuff. And what we'll do is we'll kind of go through it. Let me just go through it in words, and then you'll have to read this many times. Okay, down at the bottom here, there's a little paragraph that says the explanation is longer than the program itself. Okay, yeah. And the thing is, you need to read the explanation many times. You read it and you reread it and you reread it, and it starts slow. And as you work through it, you go back and reread it. There's a lot of detailed information in this write-up. As you're writing the code, you'll get questions. And a lot of times, if you go back and reread the explanation, sometimes that'll answer your question. So it's a long explanation for a lot of little steps, but those little steps don't add up to a lot of code. It's not a lot of code, it's just a lot of little steps. Okay. Okay, so the first thing is, what about running a job on a specific CPU? Okay, you know how to create a process. That is the create process function. Let's see, where is this? Okay, when you call create process, that's what starts a program. But when you call create process, the program will start on any CPU the operating system wants to run it on. Okay, so the operating system doesn't, your scheduler is told to only use certain CPUs, but the operating system doesn't know about that. So your scheduler has to control this. So you have to use create process in a real specific way, because otherwise it'll just launch C processes on any CPU, not the ones that you're supposed to use. Okay, so when you create a process, you can create it what's called suspended state. Okay, and you do that by setting a process creation flag. So if I open up the help documentation on create process, it has these creation flags. Okay, one of the creation flags is create the process suspended, which means don't run it. Create it, but it's halted. Okay, by telling Windows to create the process but immediately halt it, that gives you a chance to tell Windows which CPU you want the process run on. Okay, so what we'll do is we'll create the process, but we'll create the process with the suspended creation flag. So the process is started up in a suspended state. Then we're going to use a function that sets the affinity of the process. Okay, so this function here, set process affinity mask, that's a function that tells Windows, here's a process and here's a CPU, only run that process on that CPU. Okay, so if you open the help on this, see, the function takes two parameters. Here's a process, here's a CPU. Run this process on this CPU. The process, this is the handle to the process that you use, for example, when you waited for it in the last homework assignment. So that's the handle to the process. This is the Affinity Mask we were talking about just a minute ago. You write the hexadecimal value of the bit that represents the processor you want to run the process on. So you tell Windows, when you do this function call, you're telling Windows, run this process on that processor. Actually, you could run a process on 3 processors. Okay, so, but we're going to be running a process on only 1 processor. So this bit mask here will only have 1 bit in it. Okay, so you'll create the process in the suspended state. Then after the process is created in suspended state, you'll call set affinity mask to tell the operating system what CPU can run that process on. Then you have to tell the operating system, go ahead and start the process, but it's called resume. Okay, so you'll resume the suspended process. Okay, and if you look up this function, it takes only 1 parameter, but you don't say resume. This is why this stuff gets tricky. You suspended the process, but you don't resume the process. You resume the process's main thread. So you have to resume the process's thread. So now you're used to giving a handle to the process. Now you need a handle to the thread. Okay, so that's also described in here. Okay, when you call create process, it gives you back this process information structure. That's where the handle to the process is. That also holds the handle to the thread. Okay, so when you call create process, it gives you as an output parameter this process information data structure. You used it in the last couple assignments. That's where you get a handle to the process. It also holds a handle to the main thread, and that's what you send to the resume thread function. Okay, you can see how there's a lot of details here. Okay, this paragraph here is only about how to create a process suspended, assign it to a CPU, and then start it up on that CPU. So this whole paragraph describes the steps of doing that. To do that, you need to call the create process function. You need to use an affinity a creation flag. You need to call the set process affinity mask function with a handle to the process. You have to call the resume thread function with a handle to the thread. So you have a lot of information, but 3 lines of code. This is all describing 3 lines of code. 1 line of code to call create process, 1 line of code to call set affinity mask, and 1 line of code to call resume thread. Okay? But those 3 lines of code do quite a bit. So there's a lot to think about in 3 lines of code. And this is what this kind of world of programming is like. You don't think of 3 lines of code as something that takes you an hour to write, but here it does. Okay, here you can spend an hour or 2 trying to get 3 lines of code written and debugged because there's so many things going on in those 3 lines of code. Okay, now another thing that you have to worry about is how does your scheduler know which CPUs it's allowed to use? Okay? So that's actually the first thing your program does. Okay, let's actually look at the code for a second. Here's the outline of the code. I've given you a little bit of code here, and then mostly here are steps that you have to do. The steps here are in the same order they are in the web page to describe the assignment. Okay, so the description here, the paragraphs here pretty much follow the order of these steps here. Do this, do this, do this. Each one of these is going to be just a few lines of code. Every one of these little things here is just 2 or 3 lines of code. Okay, and you have to just follow through the description and write these steps. Okay, so for example, you'll have to read the job duration times off the command line. That'll be the first thing you do. Now, here's what I just mentioned ago. This is how your program finds out which CPUs it's allowed to use. Your process is going to check its affinity mask. Okay, what it is it's going to check this. This is the affinity mask that a process has. Like this process has an affinity mask of 0, 1, 0, 1, 0, 0, 0, 0. And I could change it to be like this. Now its affinity mask is 1, 1, 1, 1, 0, 0, 1, 0, 0, 0. Okay. So you here in Task Manager, you could set the bits that determine which CPUs are given to this process or not. Okay. But then when your program runs, it needs to find that information out. It needs to get its processor affinity mask. So it needs to find out what it's allowed to be using when it does scheduling. Okay, so there's this function get process affinity mask. Okay, that's a function where a running process can ask the operating system, which CPUs am I allowed to run on? Now, at any given time, we know the process is only running on 1 CPU, but it could be running, it could move from 1 CPU to another. Now, the process doesn't get to move itself, the operating system moves it, but the process can at least ask the operating system, what CPUs am I running on? Okay, so a process calls this function with a handle to itself, and then it gives a pointer to this parameter and a pointer to this parameter. These are out parameters like scanf uses. That means that this function will fill in what this thing points at. And this function will fill in what this thing points at. So these parameters are pointers to variables where this thing will put its output information. Okay. In the web page, that's explained in this paragraph here, this idea of these output parameters. Okay. So you call get process affinity mask with two parameters. Oops. You call get process affinity mask with two parameters, three actually. The process, a pointer, a handle to itself, because a process wants to get its own affinity mask, so it calls this function with a handle to itself, and then these two pointers to parameters. Okay, so it's a lot like scanf work. Scanf, when you call it, you would say scan something into this variable. Here you're saying get these affinity masks and put them into these variables, into what the locations pointed to by these variables. Okay. All right. When your program has this processor affinity mask, okay, well, it gets to, actually, it doesn't need this one. When you call this function, you get two affinity masks. This affinity mask is actually how many processors the whole CPU has. We're not going to use it. This is the one we're interested in. This is the process's affinity mask. Which CPUs is the process allowed to use? Okay. When you get that value, it's a number, but like we said before, we don't really want to know what the number is. We want to know which bits are set in that number. So we have to do a little bit of bitwise operations because we have to figure out which bits are set in that number. Okay. Like here's an example in this web page. See, that might be the actual value returned by in the process affinity mask, and you need to figure out that there's that bit, that bit, that bit, and that bit set. Okay, you don't want to know what that number is. You want to know which bits are set in that number. Okay, so you have to write a loop that steps through the bits of this value and counts the ones and denotes and keeps track of which position the ones are in. Okay, so there's a data structure that's described in here that you can use. You'll create an array of bits that are the bits that are turned on in here. Okay, so you'll get the processor affinity mask for this process. Pardon me? Do you have a question? Okay. So you'll get the processor affinity mask. That's calling that one function. Then you'll take the value in it and you'll count the number of 1 bits in it. Okay? That tells you how many processors your job your scheduler is working with. Okay? Once you know how many processors you have, you're going to create a data structure that we're going to call a processor pool array. You're going to create a data structure representing each processor. For the most part, this homework assignment is manipulating this data structure. This data structure keeps track of which processor is running which process, okay? And the web page describes it carefully, but roughly what it is, it's an array of these struts. It's an array of struts. For each processor, you want to know which bit represents it, what's the handle to the process it's currently running, and whether it's actually in use or not. A processor can be idle, so this is going to be 0 or 1. It'll be 1 when the processor is running and 0 when the processor is idle. So for a processor, we keep track of which CPU it is. Is it CPU 0, 1, 2, 3? So it's affinity mask. And we'll keep track of what process it's running. and then we'll keep track of whether it's actually running something or not with a 0 or 1. Okay. You'll create, in this step, an array of those data structures, one for each processor that you've been assigned. Okay. So all this stuff here sets up the data structures. I'm sorry. All this, these lines here set up the data structures. Then you start running processes. So now you drop into a loop where you're going to launch each of the processes that if you've got 5 jobs to run and 3 CPUs, you'll launch 3 CPU processes here. If you have 7 processes to run and 8 processors, you'll launch 7 processes here. So you launch as many processes here as you have processors. Okay. So that's the initial batch of processes. Then the tricky part is here. After you've launched the processes, you start waiting for them to die. You start waiting for a process to finish its work, so that frees up a processor and you can schedule another process. Okay, so that'll be a loop that just loops until there are no more jobs to run, till you run through all the jobs. Okay, this loop will it's basically what you're doing is here's the line. I wrote the trickiest line of code. I wrote it for you here. So this line of code you don't need to change. This line of code waits for the running processes for one of them to end. So maybe you have 3 CPUs, so you're running 3 processes. One of them is going to end first. Okay, so this is the function that'll tell you when a process is ended. What you do before, you just called wait for single object, and you would give it a handle that it would wait on. If we're going to wait for multiple objects, we have to give it an array of handles. So this is an array of handles. But in C, you never know how long arrays are. So this parameter is the length of that array. So this is an array of handles that you want to wait on, and this is how many of those handles there are. Okay. This says we want to wait forever. You could possibly wait for a short period of time and then do something else. We're just going to wait until one of the processes finish. So, okay, so what you have to do here is build that array. Okay, so this code up here is building the array of what to wait for. And that array is going to be a subarray of the processors. Because suppose you have 4 processors. You could be running a process on each one, but maybe you only have 3 jobs to run altogether. So even though you have 4 processors, you may only have 3 processes running. So you may only be waiting for 3 processes. So this code here goes through the processor pool and sees which processors are actually running. That's why they have a bit for running. If a processor is running, then it's counted, and this handle here gets put in the processor handles. Okay? So you go through the processor pool looking for running, this code here goes through the processor pool looking for running processes. For each running processor, it puts its handle in this array. Then it calls wait for mobile objects. When one of those processors ends, this thing returns a result. That's the index into this array of the process that terminated. So this is an array of handles to processes. We're waiting till one of them terminates. When one of them terminates, we get a result. The result is the index into this array. It could have been this result was the handle to the process that terminated. They didn't do it that way. This is an array of handles. When one of them terminates, you get back the index into this array of the handle that terminated. Okay. So then you have to say, okay, so now I know that there's a job that finished. I have to look up which CPU it was running in. So then you have to go back up to the processor pool. You'll figure out which one of the processes became free and schedule another job on that process. So, okay, so that'll be this code here. This code here will be schedule one more job on the processor that just freed. And then loop, build an array, wait for some process in that array to terminate. When a process terminates, figure out which one terminated and launch another process on that processor, loop again. Okay? Okay. All this talking is really just a very sketchy, I mean, it really is a really sketchy description of it, of what you have to do. There's much more detail in this write-up here, way more detail in here. Okay? So what you have to do is read this several times. While you're reading this, here's a brief outline of what it's telling you, but here you're going to replace each of these with the code. Replace that line with this code. Replace this line with this code. Pretty much each of those lines is one of the paragraphs in this description. Okay, so this description tries to step you through each of these little chunks of code. It's, as I said many times, it's not a lot of code, but it's a lot of ideas. At the bottom here, here are the functions you need to use. So, we've used create process before. The new functions here, you're going to use resume thread, wait for multiple objects, get process affinity mask, set process affinity mask, get current process, get process ID. So there's a few new functions here that you have to get used to. And there's the create process, which you've used already. Okay, so it's a lot to read, not much to write. Okay, so in the past in this assignment, people just ask a lot of questions. It's not at all, the way you should think of it is you should keep reading this and just ask questions. Show me code. You'll get stuck at certain parts. C's not an easy language to write this kind of thing in. You're going to be doing things like bit manipulation. So it will take some getting used to. Okay. Oh, and you can also experiment with the demo version. Okay. If you're in doubt what your program should do, you can run it in the demo version. You can run the demo version and see what it does and get a sense of whether yours is doing the right thing. Oh, and then there's one other thing I show you here in the demo version. We've been setting the processor affinity mask kind of the hard way. We use Task Manager to go to CMD to set affinity, okay? So we've been doing it that way, okay? There's another way to do it. You can do it on the command line. You can set the affinity on the command line, but it's a little bit verbose. So here's what it looks like. Here's an example of a command. I'm going to copy and paste it into my. Okay. I'm going to start, essentially, I'm going to start a new CMD. B means don't create a new window for it. Then the little secret sauce here is when I start this CMD, this is its affinity mask. Okay, that is 4 CPU. No, notice it's 23. Think of it. That's actually 4 CPUs. The 3 is 1 1, and the 2 is 1 0. So there's only 3 bits set there. Okay, so that's 3 CPUs. Okay, then I'm going to run on those CPUs, and what I'm going to start is time this, but time this is going to run, or I want it to run the demo version. So I'm going to time this, the demo version, first come, first serve scheduler, a 30-second job, a 5-second job, a 20-second job, a 10-second job, and a 15-second job. Okay, so this is going to run 1, 2, 3, 4, 5 jobs on, remember, this is actually only 3 CPUs. Okay, now, remember, over in the task manager, I put this CMD back to all the CPUs, but this part here, start/b/affinity 23, is actually going to run this program on only those 3 CPUs. So now I can hit enter and run, and you can see it's only running on 3 CPUs. Processor 1, processor 5. Oh, and here's the other one. There's the 3 CPUs. Now notice it's down to 2 processes on 3 processors, but there's only 2 processes, so 1 processor is idle at this point. Okay. And here's a little record of what happened. It launched the 30-second job on 1, on mask CPU with mask 1, the 5-second job on CPU with mask 2, the 20-second job on CPU with mask 20. Okay, see, 1, 2, 2, those are the 3 bits that were set in this mask 23. Okay, so this hexadecimal mask had 3 bits in it, this bit, and this bit. Okay, and then this CPU became available and got reused, and then this CPU became available again and got reused. So notice that 3 of the processes were run on 1 processor, and this processor was used for only 1 process, and this processor was only used for 1 process, and the other 3 processes ran on the same processor, and it took 33 seconds to run those. Okay, all right. So you can set the affinity at the command line if you want to type this more verbose command, or you can just set the affinity in Task Manager once and for all. Yeah, setting an affinity in Task Manager is sometimes a little bit easier, but setting an affinity over here, once you get used to it, it lets you change things. Like, I can set the affinity now to just say like 7. Okay, 7 is what? Okay, what is 7 in binary? 4, 5, 6. So that's 3 bits. I think that's 3 bits also. Okay, right. So I changed which processors are using, because I could easily change the bit mask. Almost done. Okay. Notice that took about the same amount of time. Last time we ran it, it took 33, just hair over 33 seconds. This time it took a little more than 33 seconds. And it ran on different processors, 1, 2, and 4. Okay, so the 7 was what the first bit, the second bit, and the third bit. No, I'm sorry, first bit, second bit, and fourth bit. Okay, okay, all right. Okay, now it's not easy to do questions here, so if you have, does anybody want to try to ask a question? Is there a specific question anybody can think of? Okay.
Professor,
Yeah.
question. So it's not about the homework specifically, but more about the whole online thing. So it looks like you're recording this. Are you planning on uploading this later for?
Yeah, I was going to look at how it came out, and I recorded it just as an experiment. I'll see how it comes out, and I'll try to find, I'm not sure where I can upload it to, probably YouTube. So I'll probably just be uploading it to there. But yeah, that was my hope, If it comes out good enough, then I'll upload it. And then I may try to make a streamlined, better version of it. But yeah, I do plan to try to upload this.
All right, that's all.
Okay. I mean, I hope I don't lose the recording of it. I'm not even. I have to figure out where it's even. It's supposedly recording on my computer, but I'm not sure in what folder it's going. Does anybody know where it gets recorded to? I'll have to look for the final file. Let's see. Okay.
It's gonna be in a folder specifically for Zoom. I believe as soon as the recording is done, it'll show you where the directory is.
Oh, so it'll like pop up and show me where to save it.
Yeah.
Okay.
For mine, it's in my documents folder, and then they created a Zoom folder in documents for it.
Okay. Okay. Good. Yeah, and I probably will just try to upload it to YouTube. I think that'd probably be the simplest place to put it. Okay. And then I'll give you a link to. I'll put it up on the course website. A link to where the video will be. Okay. Anybody got a question about the homework assignment? Okay.
So each command prompt window that launches represents an individual CPU?
Yes, exactly. Yeah.
Okay.
To make it easier to see what's going on, I have each CPU, each process is launched in a separate window on one CPU. Okay. So all those little pop-up windows, if you look at, if you watch carefully, see, it tells you which CPU is running that window. Okay, then see here, like this window, see, that's the CPU. It's running on CPU 1, but this window here is running on CPU 2. Okay, so each window represents one process running on one processor. Okay, you should never see this number here change. If this number here changes, then you didn't fix that process on a processor right. Okay, so when you run these, this process, it's got PID 19712. Well, okay, this process, it's got PID 2496, and he's running on processor 1, and he should stay on processor 1. Processor 1 is one of the processes given to your scheduler, and you should be scheduling a process on a processor. The process never moves. So right now I got I've got that process on processor 0, and I've got this process on processor 1. Okay. So each pop-up window represents a process on a processor. And then the scheduler itself is running in this window here. And the scheduler itself can just be running. We don't care where the scheduler itself is running. The scheduler itself could be running on any processor. That's up to Windows. We're not controlling where the scheduler runs. We're letting the scheduler control where the other processes, where its processes run. The processes that it schedules on its command line, the scheduler schedules these processors on whatever Affinity Mask it's been given. Okay. Other questions? This is not a lot of code, but it's a fairly sophisticated little piece of code. It's writing something, in a way you're actually implementing one small piece of what goes on inside of an operating system. We're scheduling it on top of the operating system, but the way you have to keep track of which CPUs are running. Then when one of the CPU dies, you have to figure out which CPU it was. When one of the processes died, you have to figure out which CPU it was running on, then launch another process on that CPU. That's a pretty sophisticated little bit of programming. So it's a nice assignment. It's not easy. It's, like I said several times, it's not a lot of code, but you're writing these kind of super densely packed lines of C code where you're calling functions with in and out parameters and doing bitwise operations. So it's kind of a level of sophistication that's newer, but it's not a lot of code. Okay. And read this assignment many times. Don't read it once. Oh, and don't think you can write this the day before it's due. Yeah, this takes a while to work on. Okay, so read it several times, read it many times, read it once you started coding, go back and reread it as you run up against stuff. Okay, all right. Let's go ahead and quit because there's not much time left. What we'll do on Wednesday is go back to the multi-level feedback queue algorithm and really talk about it. So that is chapter 8 in the operating systems textbook. Okay, so make sure you read this chapter here carefully, and we'll go back through on Wednesday and we'll really talk about that algorithm. After that, we'll start another topic. We're going to start talking about virtual memory. Okay, so this ends talking about scheduling. So probably on Wednesday, we'll be done with scheduling, and we'll start the next section of the book. Afterward, we're not going to do the lottery scheduling or multi-CPU scheduling. Okay, so we're not going to do those two sections of the book. So after the multi-level feedback queue, we'll start talking about address spaces. We've talked about them a little bit. We drew pictures at the beginning of the semester. We drew lots of pictures of virtual memory and physical memory. We're going to start refining those pictures and say real carefully what we mean by address space, address translation, and what we're getting up to is this page tables, virtual memory space. Okay, so let's quit, okay? And we'll meet again on Wednesday at 12:30. Send me emails with questions, and just I sent you an email. If you work with your friends, try to find ways to work with friends. Even if you're at home. Visual Studio Code has supposedly a way to work with multiple people. You might want to look into that, but there's something called Code Share for Visual Studio Code that can let people work simultaneously in an editor together. So you could be at home and your teammate could be at home and you could be editing code together in Visual Studio Code. So look for ways to work. There's always emailing code back and forth. You can email code back, but it'd also be nice to start learning how to work in groups together. So try to find ways to work with, communicate with me, communicate with your classmates, and try to keep up with what we're doing here. Any last question? Okay, so I guess I'll just end the meeting. Does anybody want to chat with anybody that they're chatting with, or should I is it okay to just close it? Okay. Okay, so I stopped sharing. Okay, I'm going to end the meeting. Thanks for coming. Bye.